that every question that you do with forces is ultimately the same thing as long as you get your force diagram correct. So does anybody want to tell me then, we've got our 5G newtons, which is the weight of this object. Remember, the weight is the mass multiplied by the gravitational pull, right? So it's mg, and g here we take as 9.8 meters per second square. Now, for anyone who studies physics, you use 9.81, but in maths we use 9.8. It's important to get that absolutely right. So when we say 5G here, we literally mean 5 multiplied by 9.8. All right, and if we work out 5 multiplied by 9.8, which is 49, that's the force. Okay, 49 newtons, 5 times 9.8. That's the force that's acting down through the center of the object towards the center of the Earth. Now, the force that's opposite to that, which is R, that's the normal reaction force. That's the reaction force that stops the object from either sinking or taking off. All right. Every action has that equal and opposite reaction. So those forces are already labeled in. If they weren't labeled in, your job is to label them in. All right. So if you got a question where they're not there, you've got to put them in. And the weight always goes directly down the page, always directly down the page. And the reaction always goes perpendicular to the surface that the object is sitting on. Right, and that's important because they're not always opposite each other, as we'll see in a minute. And then we've got this 2 newtons, which goes off at an angle. Now, anything that's off at a diagonal, remember it's doing 2 things. Okay, if you imagine placing an object on the floor and tying a string to it and holding it in your hand, and you pull the object across the floor, you're actually doing 2 things. You're trying to pull it across the floor horizontally, but there's also an element of that force that you're exerting, which is ultimately trying to lift the particle up. You see what I mean? Right? So there's a horizontal and there's a vertical. So wherever we have a diagonal force, we've got to split it up into its horizontal and its vertical. So bearing that in mind, does anybody feel confident enough to split this 2 newtons up into its horizontal and its vertical components? Matthew, your hand nearly went up. Okay, tell me how you got root 3. Perfect, right? So what we do is we've got 2 multiplied by cosine of the angle, all right? And that comes from a right angle triangle. It comes from SOHCAHTOA, right? Sine is opposite over hypotenuse, cos is adjacent over hypotenuse, and tan is opposite over adjacent. So when we've got a force which is adjacent to the angle, we take the magnitude, which is the hypotenuse of this little right angle triangle that you can imagine, take the hypotenuse, the 2 newtons, and multiply it by cosine of the angle. All right? Follow? Now, I want you to label those forces in your diagrams always, and you should, whenever you're splitting up and resolving a force like this, use a dashed line to show it, okay? Use a solid line for any forces that are absolute, and then use a dashed line for anything that you have split into components. So that means that's the horizontal component. What's the vertical component using the same logic? Someone else? To sine 30. Okay, perfect. And again, using SOHCAHTOA, all right? This force, this whole vertical component, sorry, is opposite the angle, so it's the hypotenuse multiplied by sine of the angle, right? Okay, so we've got all of our forces. There's nothing else to resolve here, okay? We're not talking about any friction or anything like that. We'll introduce friction a little bit later. Well, we'll do an example with friction, but we go into friction in more depth just before Christmas. And then we have a look and say, okay, it's lying on a smooth horizontal floor. Now that word smooth, incidentally, why is that really important? Why is that word there really important, Ruben? It means there's no friction, okay? And you're looking out for that sort of stuff. If it says rough, for example, then it's got friction, and you're going to have to work in a slightly more complex way. All right, smooth means no friction. It's pulled by a force of 2 newtons, blah, 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 causing the box to accelerate. Now, there's another key word. So when we're talking about acceleration, what did we talk about last week in that kind of terrible lesson that all went wrong about acceleration? What do we know about acceleration in these diagrams? Hassan? It's a resultant force, right? So there is a resultant force. What's the equation that we're going to use? Whose law is it? Yeah, Newton's second law. Okay, so we're going to use Newton's second law. And Newton's second law says F equals ma. Resultant force equals the mass of the object multiplied by its acceleration. Now the resultant force, we're already good at working those out. That's the sum of all the forces, okay? What that means is, if you have a, this is my classic example, we looked at this, if you have a particle which has got two forces exerted, 30 newtons going up, 20 newtons opposing it going down, which direction is that particle going to move in? It's going to move up, isn't it, right? Because the up force is bigger than the down force. So it is going to accelerate upwards, and its resultant force is going to be 30 minus 20, which is 10 newtons. Okay, so the resultant forces is just basically when you add up and subtract all the forces that you've got going on. All right? Okay, so now we need to tell the examiner or the reader which direction we're going to work in. We're talking about acceleration here, so it makes sense to resolve horizontally across the page, because if you look at this object, it's going to accelerate off to the right, isn't it? That's what's going to happen. If you actually did this to an object like that, it would accelerate off to the right. So we're going to resolve to the right, and I want you to get used to using this notation. Capital R for resolving, and then an arrow to show which way you've decided is positive. All right? Yeah? Okay, so what are the overall forces that are acting horizontally here? How many have we got acting to the right? What's the magnitude of the forces going to the right? Tom? It is just 2 cos 30, right? The only force that's pointing to the right of the page here in any way is just that 2 cos 30. Remember, this 2 newtons we've resolved, so it's just this 2 cos 30. Is there anything going in the opposite direction, to the left? No, there's nothing. All right, so our resultant force, although we did it in this example to the right here, 30 minus 20, there's nothing opposing that 2 cos 30. So 2 cos 30 is our resultant force. Okay, 2 cos 30, and there's nothing to subtract. There's nothing dragging it the other way. Now, the mass, 5 kilograms. Don't get confused with the mass and the weight. The mass is 5 kilograms multiplied by the acceleration. And so the acceleration is just going to be 2 cos 30 over 5, which someone with a calculator, what does that come out as a decimal? And remember, your calculator needs to be in degrees. Anyone? 0.35. Can I get corroboration from another person? Yeah, we're all good. So 0.35 meters per second squared. Don't forget your units. And then if you look at that, 0.35 meters per second squared, does that kind of make sense? It sort of does make sense, all right? If you've got an acceleration of 25, for example, that's a lot. That means it's getting 25 meters per second faster every second. That's a really crazy acceleration. 0.35 seems to be a sensible number. Okay, so then we're being asked to work out the normal reaction of the box with the floor. Now, the normal reaction force we always get when we resolve in the opposite direction. Okay, so we're resolving perpendicular to the surface. I never ever say up and down really anymore with these questions. It's perpendicular to the surface. There's the surface, there's perpendicular. So if we do it again, we're going to use F equals ma, right? That's it. We're always using F equals ma. Now, what's the resultant force? It's going to be R minus 5g, isn't it? Yeah? If I resolve up, if I see up is positive, I'm going to have R minus the 5g, very much like this 30 minus 20 example over here, right? R minus the 5g equals, and this bit is going to seem a bit pointless, but equals the mass times the acceleration. Okay, the mass is 5. Is the particle accelerating in the vertical plane? It's not, is it? It's only accelerating horizontally. It's not being lifted up. If it was accelerating vertically, that particle would come off the floor, which it's not going to do. So equals 5 times 0. All right? So it doesn't have an acceleration vertically. Ellis? Oh, yeah, we forgot about that, didn't we? Yes, 2 sine 30. There we go. That's me getting ahead of myself again at 8:30 in the morning. So you're absolutely right. Where does it go, Ellis? Absolutely right. Okay. R plus 2 sine 30, and then I'm going to do minus 5g equals the 5 times 0, because it is f equals ma. All right. So we've got R plus 2 sine 30 then equals the 5g. And then so R gives us 5g minus 2 sine 30, which should come out at 48 newtons. We just double check that. Sine 30 is a half times 2 is 1. 5 times 9.8 is 49, so we should have 48 newtons. Yeah? Good. So that's it. That's resolving forces with F equals ma in its kind of most basic form, I would say. All right? So I want you to have a go at this question. It's very similar. Okay, it's almost identical, but I just want to highlight one difference first. Well, two differences. First of all, the only force that's been drawn in is T, all right? So you need to think about where's the reaction force and where is the weight. The other thing is, I really just want to highlight here is, this is not a smooth surface, it's rough horizontal ground, and there is a frictional force of 12 newtons. Now, we're not going to talk much about friction at the moment, other than which direction would that frictional force be acting on the block? Which way would it be going? Left, right? It's going left because you're trying to drag something right. The frictional force is trying to stop you, so it's going in the opposite direction. So before I let you loose with the question, I'm just going to give you a bit of a head start, and I'm going to say you've got 12 newtons going off to the left there. Now, over to you. Have a go. Give you a few minutes, and I'll put the answer up on board, okay? So the working and the answer are there. Hopefully you can read it. I'll switch the light off just because you can't see it. So I've added the forces in red with dashed lines. We've got the 12 newtons over to the left. I added in the middle. We've got T cos 30, which is horizontally to the right. We've got T sine 30, which is vertically up. We've also got the normal reaction force, which my diagram doesn't do it justice, but it is perpendicular to the floor. And then we've got 10g newtons, which is the weight of the object, which is acting directly opposite to the normal reaction force. Okay, so that's my force diagram. We're being asked, you know, we're given an acceleration this time of 0.4. And so I decided to resolve horizontally first. All right, it seemed to make sense. So I resolved horizontally at the top. You can see my capital R with the arrow to the right. F equals ma. My forces are T cos 30 to the right minus the 12. And then I've got equals 10 multiplied by 0.4. 10 kilograms multiplied by 0.4 acceleration. Simplify it down and solve the equation. You get the tension is 18.5 newtons. Okay, we'll aim for 3 sig figs. Once we've got the tension, which is one of the things we were asked to work out, we'll resolve vertically, and we've got R plus T sine 30. Those are the two forces that are going vertically up the page. And then we're going to subtract the 10g, and that's equal to 0 because there's no acceleration vertically. And again, rearrange carefully, substitute your value of T in, use the one from your calculator, not the rounded one, and then solve to get R, which comes out as 88.8 newtons. So can I see a quick show of thumbs on success ratings with that question? Thumbs up for success, thumbs middle for just about, and thumbs down for nope. Okay, good. So right. So across the board, we will need practice at this, but does anyone want to ask any questions about that? Why I did anything? No? Okay, cool. Right. We're going to look at a slightly different question now. Okay, we're going to look at something where all of a sudden we're not on horizontal ground. Okay, so the first thing I want you to do then is to copy that diagram down, and I want you to have a go at adding all of your forces in. I want to see all the forces in your diagrams in the right places. So we're given a diagram. Does anybody want to explain to me then what forces we've got acting on this and where we should put them? Ruben. Perfect. Okay, so we've got a particle of mass 2 kilograms. And so from the particle here, directly down the page, obviously not squint like mine, we've got 2g newtons. Okay, always directly down the page. It's not perpendicular here, it's directly down. Anything else we can add in, Hassan? Lovely. We've got R, which is perpendicular to the surface that it's sitting on. Now, one of the biggest mistakes that people make in an inclined planes question is to have R and the weight going in almost like a straight line opposite each other. That's not the case anymore. Remember, R is always perpendicular to what it's sitting on, and the weight is always vertically straight down to the center of the Earth, effectively. What else have we got going on? Not much. Not much. Right, what are we going to do about this 2g newtons? Because in the last example, whenever we had a force that was diagonal, we had to split it up into its components, didn't we? Because it was doing two jobs. It was trying to drag it along the ground and lift it up at the same time. If you look at this diagram carefully, we've got another diagonal force, haven't we? This 2g is almost like the equivalent of that diagonal force. If you tilt your head a little bit and pretend that this is flat on the ground, then this all of a sudden is a diagonal line. We need to know the magnitude of the force that is directly opposite to the normal reaction force. We need to know what size that is. Okay? Now we also need to know this force, which is parallel to the plane, because this 2g is doing two things. It's effectively pulling the object P into the surface a little bit, but it's also pulling it down the surface a little bit. That's what the weight of an object does, isn't it? If you actually did this in real life, that weight is going to try and pull it down the surface, but also keeps it on the ground. So we need to work out what these two things are. Now, what helps us is always and forever when we do these questions, this angle in here, because you know that when we split this up into its components, we're going to need to use sine and cosine. But the angle in the middle is always the same as the angle down here, always. And we can prove that using right angle triangles, all right? But it's always the same. Now, this side here, one question. Is it adjacent to the angle or is it opposite the angle? And I'm talking about this angle. Adjacent or opposite? Adjacent. And what trig ratio do we use when it's adjacent? Cosine, right? Adjacent, K from SOHCAHTOA, cos adjacent hypotenuse, K. So we're using cosine. And what we do is we take the weight, which is 2g, that's the force. We've got 2g this time, and it's cos of this alpha, right? Always. Always. This one is always cosine, and you take the weight and you multiply it by cosine of the angle. Now, we'll get to what this is in just a minute. So this one here, this is the question. Is this force here parallel to the plane? Is that opposite the angle or is it adjacent to the angle? It's opposite, right? And so it's opposite the angle, we're going to use sine. So we're going to take the 2g, again, the weight, and we're going to multiply it by the sine of the angle. So we've got this force and this force now. The 2g has been split up into its two different components. Does anybody want to ask a question about that? Okay, good. Right. We need to know what sine theta and cos theta are. Are we given it in the question? Kind of, yeah. We're given tan theta equals 3/4. Now, we can use that in two different ways. The way that I don't recommend that you do it is to work out what the angle is and then use sine. All right, so you could say, tan alpha is 3/4. You could do shift tan of 3/4, get the size of the angle, and then do sine of that and cos of that. You don't need to, right? There's a little trick that we can use here. Imagine any generic right angled triangle, right? Just any general right angle triangle. There it is. We'll put the angle where we're quite used to seeing the angle, down in the bottom left corner. If tan of the angle is 3/4, remember from SOHCAHTOA, tan is opposite over adjacent, right? Remember that? Right. So if it's opposite over adjacent, it means the opposite side to the angle is 3 and the adjacent side to the angle is 4. Now, this triangle doesn't exist and it's got nothing to do with our diagram. This is just a way of finding out what sine alpha is and what cos alpha is, because we need those. Now, sine is opposite over hypotenuse, yeah? Cosine is adjacent over hypotenuse. So we need to know what the hypotenuse is. How are you going to work out from this right angle triangle the value of the hypotenuse, and the magnitude? So, yeah, Pythagoras theorem, okay? It's a 3, 4, 5 triangle. 3 squared plus 4 squared is 5 squared. And so you use Pythagoras theorem to work out that that's 5. Pythagoras theorem, by the way, keeps coming back. You will use it a lot over the next 2 years. All right, so now that allows us to work out sine alpha. Sine alpha then is opposite over hypotenuse. It's 3/5. And cos alpha is adjacent over hypotenuse. It's 4/5. Now you might be given that in a question. It might just say tan of this is this. If it gives you the angle in terms of tan, sketch a general right angle triangle and fill in the blanks. Right, now we've got everything that we need. We're being asked to work out the acceleration of the particle. Let's resolve. Okay, that's what we're going to do. And we're going to resolve parallel to the plane, by which I mean kind of up and down the slope. So my little arrow this time is going to go like that, diagonally up. Yeah. So resolving diagonally up. We're using F equals ma, resultant force is mass times acceleration. And the resultant force, remember, is all the forces that are acting up minus all the forces that are acting down. So I'm only looking in terms of this diagonal line. I've got a 4 Newton force which is going up the plane. It's the only one that's pushing this thing up the plane. And then I need to subtract any that are trying to drag the thing down the plane, which is this 2g sine theta. All right, so remember, even though I've drawn it down here, that's just because right angle triangles help us to visualize the magnitude of the force. The force is actually acting on the particle, trying to push it down the plane. So we've got 4 minus 2g sine theta. Are there any other forces there that I've missed out? Can't see any. Okay. Equals mass times acceleration, all right? The mass is 2, and the acceleration is what we're being asked to work out. Right? So let's divide everything by 2. 4 minus 2g sine alpha divided by 2 gives us the acceleration. Sine alpha we've worked out as 3/5. So we've got 4 minus 2g times 3/5, all divided by, not divided by a, divided by 2. Equals the acceleration. And you can whack all that in your calculator. Okay, don't forget that g is 9.8 meters per second squared. So let's have 2 people give me an answer for that. Hassan. Yeah? Yeah. 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 Right, anyone got an acceleration for me? Go on, shout it out. If it's wrong, doesn't matter. Sorry? 1.4. Did anybody else get 1.4? Still working it out? It's all right if you got something different. It could be that Matthew got it wrong. It's all right, and it's fine to get things wrong. So 4 minus 2 lots of 9.8 times 3/5 divided by 2. Minus 3.88. Yeah? Minus 3.9 because it looks a bit neater, meters per second squared. Now, what does that mean for this particle? What's happening to it? It's accelerating down the plane, okay? I said that up the plane was positive, all right? But actually, because our acceleration came out negative, that just means that this particle is not moving up the plane. It's moving down the plane. Okay? Brilliant. Now, we weren't asked about R or 2G and using R or 2G cos alpha, but we could have worked out the normal reaction force to this if we'd wanted to, or if they'd asked us to. But they didn't. So we're done. Right, again, similar question for you. This is the first question from the worksheet that I've put on Teams. There's no diagram. So you're going to have to draw this diagram as accurately as you can and add in all of your forces. Go. So in this question, you were asked to A, draw the force diagram, which we've just discussed. You only need the 3G and the R to get the marks for it, but you will need to resolve the 3G in order to answer the rest of the question. Work out the normal reaction between the particle and the plane, but it's asking about the normal reaction, so it makes sense to resolve perpendicular to the plane first. Okay, so we resolve perpendicular to the plane, F equals ma, R minus the 3G cos 20 that we've put in equals 0. So R equals 3G cos 20. And when you evaluate 3G cos 20, remember G is 9.8. You get R is 27.6 newtons. So then for part C, find the acceleration of the particle. Again, using F equals ma. I probably should have written in F equals ma, but that's what we're using all the time with these. We've got, in order to find the acceleration, that's when we're talking about parallel to the plane. Okay? We're actually interested in what the particle's doing on the surface. So we're going to resolve, and I've resolved down the plane, you can see here, rather than up the plane, because the language in the question literally says it moves down a smooth slope. So I've resolved down. The only force moving down is 3G sine 20. There's nothing to subtract there. There's nothing pushing it up the slope. So that's equal to 3 times the acceleration. Hold on a second, Ruben. Divide both sides by 3. G sine 20 equals A. Remember, G is 9.8, and you get A is 3.35 meters per second squared. Ruben. Because we're using F equals ma. The resultant. Yeah, the mass is relevant. Yeah, the resultant force is proportional to the acceleration, and the constant of proportion is the object's mass. Okay, we're always directly applying this F equals ma formula. That's Newton's second law. That's a kind of proven physical thing that we draw on to answer all these questions. Is that all right? Right, that's it. Okay, that's the extended version. That's what we probably should have done on Thursday. The questions are in teams. The first question that's on the sheet is called resolving forces. The first question that's on the sheet is the question that is here on the board. That's the one we've just done. So start from question 2 and see how you get on. All right, we're not in a rush to do this. This is important because this is on the test next week. So I just want to make sure that we've directly covered this. Anything that we don't manage to fit into this week, we had a long discussion yesterday, teachers, about logarithms that we're doing this week, and we feel it's a lot for 1 week. But we've got a bit of time towards Christmas that we can use as a bit of a buffer. All right? Okay, on you go. Ask for help as soon as you need it.